Okay, so from last week, okay, one of the things that we talked about, we left this up here on the board kind of as a road map, that one of the aspects that we want you to realize is that what's actually happening to these elements when they're going from one side to the other. Are they gaining electrons? Are they losing electrons? And when they are they oxidized or are they reduced? So in that process, you have to know the charges of everything. And with that, they some, again, reduce in numbers, others will gain in numbers, and that's what we mean by some get oxidized and then some can get reduced. Okay? So when you're looking at this, okay, because we're going to be talking about some of these reactions that have these abbreviations. Didn't mean to do that twice in a row. I meant to do this. It will mix them up a little bit.
Would it be single replacement, combustion?
Okay, so single replacement, combustion, synthesis, double replacement, and decomposition. Okay, so the clue that we gave when you were a freshman when you took this, if it's a single replacement reaction, it means you probably have one element or one metal that's all by itself, or something that stands alone. A combustion means you're going to have a hydrocarbon combining with oxygen, so it burns. Synthesis means you're making something. Double replacement means that you have two compounds that are possibly flipping with each other. And then, again, decomposition is when something is breaking apart. So this top one that we covered last week, what would you think that this one would be? That is a single replacement reaction, because one of the things that happens when we talk about stoichiometry is that we may say in a single replacement reaction, you may have hydrochloric acid and lithium is added to it, and what are your byproducts for that? Because you may want to know that if you have 15 grams of hydrochloric acid, how many grams of lithium chloride are you going to produce? Then when we get into a little further into the spring semester, I always say the same thing. Like it or don't like it, I think you'd like to know what is possibly in store for you. But when we talk about stoichiometry, that's going to knock you down. And gas stoichiometry will finish you off if you don't get yourself up, dust yourself off, and keep moving forward. Because the gas stoichiometry is a little more complex and a little more difficult because it's something that is new to what we've learned this year. Because one of the things that we have done before is we haven't used an equation, but we have used a compound. And what we mean by that is maybe we would say if you have 45 grams of HCl, okay, how many grams of that is hydrogen? That is a type of stoichiometry problem. It's composition stoichiometry, not reaction type. If you have a chemical reaction, then you're dealing with reaction stoichiometry. But if you had 45 grams, of course, we know that, now this is just old news, you would take your amount here, 36.45, that would be a mole, and then for every mole of HCl, this third step we said was so important because it allows you to convert what you have into what it is that you're looking for. And then finally, 1.01 grams. Because you're just dealing with one substance here in composition stoichiometry. Later on in this semester, we're going to be talking about reaction stoichiometry, where you're taking one substance and predicting how much of this you're going to make. It's a very similar process to this, but you're going from one side of the reaction to the other, or you're dealing with different compounds. That's what gets to be a little tricky. If you can't, well, I shouldn't say can't, but if you're not good at balancing these reactions, it just totally makes this a little more difficult to do. It just does. There's just no other way of pointing that out, okay? And then with gas stoichiometry, this goes one step further to where now you're taking a solid substance and trying to convert how many liters or how much volume of gas is given off, which is a little brand new. See, what I'm erasing now, we're maybe just a little familiar with. It's that gas stoichiometry that's just a little more difficult. Okay, so let's take a look, see what's happening here. In order to do this, you have to know what the charges are for everything. We always would say go by your negative ion. So we don't know what iron has for charge, but we should be able to figure that out. How could we determine what the charge of iron is? Right, because the chloride ion has a charge of what? Okay. And then how many of them do we have?
3.
Okay. So this is -1. Altogether, we've got -3. That's going to be important. Okay. Then not so much for this reaction, but it will be for this one down here. So we're always going to try to take these into a progression. So if this side is -3, then this must have to have a charge of positive what?
3.
Okay. Then when we jump over to this side, what charge might that iron have now?
+2? No. Anything? +1.
What do you mean by anything?
It can be +1, +2.
Okay, but is it binding with anything?
No.
Okay, right, because this isn't bonding to anything, so it had a charge of 0. Hydrogen's only bonding to itself, so it would have a charge of 0. So if that's the case, that's what we would put here, okay? Then what's the charge of this chlorine now? Notice how I said that, chlorine. I didn't say chloride. I said chlorine. It is a gas. And it's diatomic. It's not the only diatomic molecule that we see up there. That's another clue.
It's not bonded with anything?
Correct.
Other than itself?
Other than itself. It's not 1.
-1?
No.
0?
Why would it be 0? You're right.
Bonding with itself?
Right. Because hydrogen's bonding with itself here too. So therefore, that's why we leave that up there. This has a charge of 0. Okay?
I don't get how the Fe can have a +3 on one side and then a 0 on.
It's because it's not bonding with anything.
Yeah. You could go, maybe it would make more sense if we go this way. Okay? Now we're going to do a synthesis reaction instead. So this goes all the way back to, if we did our electron dot diagrams, we know what column is chlorine in.
7.
The 7?
Okay? So then how many valence electrons is that?
7?
Okay? So then that must mean that each one of those chlorines wants how many electrons?
1.
So we could do this, and we could do this. Then, so we just created a bond, and then we would do the same thing all the way around. So that must mean, how many dots does iron have?
6.
Dots?
Oh, 3.
Okay. So that must mean that how many electrons did it give away to the chlorine?
3.
Okay. So what happens is if it gave away 3 electrons, now it's 3 electrons short. So it has 3 more protons than it does electrons. That's where that number comes from. So therefore, for every one of those chloride ions that had a charge of -1, you've got one of them here, you've got one of them down here, and you have one of them over here. That's why that overall charge now is -3, because you've got 3 of them. So then, because you're the one that asked this,
Yeah, no, I don't know. Yeah,
well, is there something interesting on there? Then,
no, that was not.
okay. So then, I see this is flashing here. So I thought I'd better keep an eye on it. Okay, so then what this must be saying is that's why we said you can put boxes around these if you wanted to. That just would only reinforce then how many electrons are around that iron now.
None.
None. So that must mean it has a charge of 0. Okay? And that's where that comes from. Whether you would say it's going to be a decomposition reaction, or if it's going this way, you could say it's a synthesis reaction. It's a little more complex to say when this is decomposing into its assorted elements. You might say, well, where do those electrons go? Well, it's easier to see in a synthesis reaction as opposed to a decomposition, I suppose. So it's just one of those things where we would say, you just accept that it had a +3 charge. It now has a charge of 0. Okay. But let's go ahead and go back to here. Because eventually what happens is when you do oxidation reduction reactions, you account for the electrons on both sides in a different manner. But we have not learned that yet. That's quite a ways off. That's a little more towards next semester. But this is something to help you in that process. Because really what we're doing is not just classifying equations, we're balancing equations, and we're writing the net ionic equations then as well. Okay, so now that we have these charges on here, okay, now this is just illustrating that this adds up to 0, okay, because this concept we're going to use down here. Okay, so if this had a charge of +3, okay, remember here are your 2 anacronyms. Okay, what is that? Remember? It is oxidation, but oxidation, loss of electrons. This is reduction. Electrons are gained. Okay, so from one side of the reaction to the other, okay, what happened with this iron? Did it lose electrons? It did. How do we know that? Well, there's 3 on this side, 0 over there. So those 3 electrons are gone. Again, we will compensate for those at some point, but that's where you're actually writing out the oxidation reduction reactions and you're balancing the charges and everything. We just have not learned that yet. We just want to establish what these charges are and what's happening. Okay.
Electrons have a -1 charge.
They do.
So if it's 3 to 0, would it be gain 3? No, look at the arrow though.
What you mean with the iron?
Yeah.
Okay.
Is it gaining 3 or losing?
It lost 3.
It lost because the arrow's going this way.
Well, it's not so much that the arrow's going this way, but it's based off of what we just did here. Okay? Because remember, this had 3 electrons. It then lost them. Okay? That's all we want you to know. Okay? And that's it. We're not going to say, well, because when you say gaining, later on next semester I'd be led to believe that eventually you're going to write something like this, +3 electron minus, to compensate for what's actually happening here. But that's an advanced concept that we're just not quite ready for. All right. So then what we see here, we see -1 is this number getting bigger or smaller?
Smaller.
Bigger.
It's getting bigger. 0 is bigger than -1. So in this case, this gained an electron. So therefore, this one was reduction. This one is oxidation. Okay? Then, and we've said this before, what type of reaction is this when things break apart? It's a decomposition reaction.
DR. Sorry, I'm so dumb.
Okay?
I don't know why.
Then the next thing we need to do is, okay,
Balance them?
need to balance that. We can't start with the ions because that's 1 to 1. So then if these come in pairs, this is an odd number. We need to get that up to an even number.
So put a 2 in front of iron and chloride.
Yeah, that's a good idea.
And then, a
Just-
3 in front of,
Distribute that through the entire compound.
and then you put a 3 there.
Yeah.
And then you put a 2 in front of iron.
There we go. Okay? So it's now balanced. Okay? But it's not balanced ionically. Those are two totally different concepts. Okay? But we do have this as a balanced chemical reaction now. Okay? So throwing this little extra information in here might be throwing you off, but hopefully it's not too bad. Okay?
I like it.
I'm good if we do more.
Okay? So, we're not running short on time yet, but see, that's the,
I don't do anything and I'm tired.
I want to say not the clue, but I don't know what the right word I'm looking for there.
I have a question.
Can I answer question really quick?
Yes. Okay, yes. Okay, so now we're going to write this out. What's the symbol for lithium?
Li.
Okay, and bromide is,
Br.
okay, and then we're adding some calcium chloride, which is,
Yeah.
and then chloride is,
Cl.
okay. Do we need to change anything with this?
I don't know. No? Well, you have to add the charges, right?
Okay,
Roll.
negative,
1. +1?
okay. So then go by your negative charges.
-1? +1. Right?
Are we sure?
+2.
I hear +1, I hear +2.
We'll go with plus.
I think we'll go with +2. Does this add up to 0?
No. Chloride has some.
This doesn't add up to 0?
Oh, that does, yeah, sorry.
Okay. Then does this add up to 0?
No.
What's your least common multiple?
2.
So what's 2 divided by 2?
1.
And 2 divided by 1?
2.
Okay. Then if we're saying this is a double replacement reaction, where does it split apart? Well, between the positive and negative ions. Okay.
Lithium chloride and.
So you have lithium chloride.
For this one, would you have to like know it's a double replacement?
Yeah.
You'd have to be told that. And then what do we have left over?
Calcium bromide.
Calcium bromide.
Now, do the charges have to stay the same?
Charges would stay the same.
Sweet edge.
Are we done on that side then?
You have to have an extra bromide.
You do. Because again, -1 plus 1, -1 plus 2. So we have 2 of them. Okay? So this is where this gets to be, perhaps you could say, a little tricky. Because now we're going to apply this same concept. Did you forget already?
No, I was trying to focus on what you're saying.
Well, then, you decide what you want to do. Okay.
Well, I know.
So we're going to apply this concept that we did up here, okay? So this one would be a little more tricky because what's happening to this bromine? over here, all the bromines have a charge of negative what? What's happening over here? It's negative 2. Now, it's not just the charge of that, but it's the overall charge of that anion. Okay? Is that the only time that happens somewhere?
No, it happens like
It happens in another spot with the chloride. Okay? Because there's only one over here, but here we have what? Got negative 2 of them. Okay. So, this is where this gets to be a little more tricky. Okay? Did anything happen to the lithium? No. So that's what we call a spectator ion. It's an ion because it still has a charge, but it didn't do anything. It didn't take part in the reaction. It was a +1 on one side and a +1 on the other. Can we say that for another ion that really did not take part in the reaction? Calcium. So we'll just put Si and Si. We'll just do it on one side because we can see it on both sides where it's what we call a spectator ion. It's just sitting there cheering on saying, way to go. Yeah. Way to go bromine. Way to go chlorine. I don't know. That just sounded good. Okay. So again, this makes this a little more difficult because now we've got a -1 here. And then what about the bromines on this side? It's -2. So did that number get bigger or smaller?
smaller.
Sure?
It goes from -1.
It does. It got smaller. Yes, what?
The rest of this, you're just balancing out, right?
Soon,
So,
yes.
The rest of this,
Slim talk.
on this one.
Okay.
Okay, yeah. So then -1 to -2, it's certainly getting smaller. Okay, so therefore, is that charge reducing? Reducing means it's getting smaller. So therefore, this one is reducing. Okay, then this one, okay, if it's getting, where am I at here? Okay. Then we have that. Because now, here's the roadmap that you can utilize, okay? Look at what we see happening here. We had +3, it's getting closer to 0, right? So therefore, it's oxidizing here, right? So if this is -2, it's going down to -1, would we say that's getting closer to 0? Mm-hmm. Yes. So therefore, this is oxidizing, and therefore this one is reducing.
Wait, but the chlorine is going up one in the charge.
You talking about here and here?
It's going from -2 to -1.
Right.
Yeah, that's oxidation.
But at the top, it's going from +3 to 0, like the one above it. So you're losing
You're talking about this one?
the other one. The
Right, right. Because here, okay, so it's losing electrons, so it's getting closer to 0.
So if it's getting
Okay.
closer to 0, it's getting oxidized.
Yes. Okay? So there's a lot of moving parts to this, and it just, I understand, it's a little more,
Because oxidation is losing electrons and reduction is gaining when it's confusing, because reduction means lose kind of.
Mhm.
But like it's, like if you do it through the REG,
reduction is gaining,
yeah.
yes. So that's another way you could look at this gained an electron. So therefore, it's got to be reducing. Okay.
It's confusing because it's reduction.
All right. So the last thing we would do is just balance this, and I think that's probably enough for today. And probably it's a little more difficult because this is new material, okay? And that's just challenging your minds whether you like it or not. Because, for instance, how many of you, this isn't the last time you're going to see this. You're going to see this again in college. And then it's one of the things we would want to spend time in high school for those individuals who do take this in college, then maybe a little more familiar with it. But otherwise, if it's the first time you've seen this, oh my gosh, that's probably pretty difficult. Okay, so quickly, let's wrap this up. We've got 2 chlorides over here and only 1 over here. How do we get more chlorines?
I
You
know,
add 2?
trust.
Okay, then I bet you we have to just add a 2 over here, and that's probably it.
Yes. Yep.
Now we got it balanced. Okay, that's all I have. We will catch up to you next time.